Earlier in the chapter, we said that physical quantities can be divided into base quantities as well as derived quantities. Physical quantities can also be divided into scalar quantities and vector quantities. Vector quantities have both magnitude and direction. Scalar quantities have only magnitude. They do not have direction. For example, the velocity of a car 25 meters per second to the east is considered to be a vector because it has magnitude and direction. Without a direction specified, then it is considered to be a scalar, where we only need to consider the magnitude. The table here has a number of common scalar and vector quantities that you encounter in the syllabus. Do bear in mind that electric field strength and magnetic field strength is something that you will really only see in A2. The rest of the quantities listed here is something you will eventually encounter in the syllabus, and you will have a better appreciation of what they mean. Vector quantities are often represented as arrows whose length and direction represent the magnitude and direction of the vector, respectively. What do I mean by that is that if you have a particular vector, you will just draw it as an arrow. The length of that arrow will represent the magnitude, and the direction in which it is pointing to represents the direction of the vector. When two or more vectors act, a resultant vector may be used to represent the combined effect or action of the separate vectors. Consider an object right now. There are two separate forces acting on it, forces F1 and F2. The combined effect of these two forces can be represented by a single resultant force. To find a resultant vector, it is done through vector addition. Consider force vectors A of 30 Newton, B of 15 Newton. Find the resultant force R for the following cases. The first case being vectors along the same line or parallel to each other. In such cases, magnitude of the vectors can be added or subtracted directly. When the vectors are in the same direction, the magnitudes are added directly. 30 plus 50 gives us 80 Newton. However, when the vectors are in opposite direction, one of the magnitudes is subtracted from the other. In this case, 30 minus 50 gives us negative 20 Newton. Bear in mind that one of the vectors has a negative sign right now. A negative sign is assigned to vectors that are acting opposite to assume positive direction. As you know, vectors have direction. When we are dealing with calculations that have vectors, we need to assume a positive direction. In the case here, we assume that going towards the right is positive. So, the 50 Newton right now is acting in the opposite direction to this assumed positive direction. That's why it has a negative sign. And it's because of this negative sign, there is the impression that one magnitude is subtracted from the other. For vectors in different directions or non-parallel directions, vector addition may be done through the following methods to take into account the different directions. The first method we will learn is the scale vector diagram method, which involves drawing the vectors in the diagram such that the resultant can be determined from the diagram itself. We first need to set appropriate scales before drawing any of the vectors to scale in the correct orientation. It's important to note that the vectors must be drawn from head to tail, which means that where the arrowhead of a vector ends, we need to start drawing the tail end of the next vector. To give you a better idea of what we mean by drawing from head to tail, consider the two vectors here, vector A and B. When these vectors are drawn from head to tail, it could look like this. Vector A is drawn first, followed by vector B, or vector B is drawn first, followed by vector A. Both of these cases are considered to be drawing from head to tail, because you will see that where vector A ends is where vector B starts, or where vector B ends is where vector A starts. If you were to have drawn the vectors like this, where vector A is here, and then vector B is here, or maybe vector A is here, and vector B is here, this is not considered to be drawn from head to tail, because you see here, the end of vector A is the end of vector B. The start of vector A is the start of vector B. So it's important to draw the vectors from head to tail before you can proceed any further. Once you have done the drawing from head to tail in the correct scale and correct orientation, the length of the remaining gap that you see is the magnitude of the resultant vector. To find the direction of the resultant vector, you will need to look at the direction from the start of the first vector to the end of the last vector. In other words, look at the direction from the first point to the last point. Applying what we've learned to an example, we have vector A at 30 Newton acting horizontally, vector B at 15 Newton acting at an angle of 40 degrees to the horizontal. We're interested in finding out the resultant force. Under the scale vector diagram method, we must first set an appropriate scale before we can draw any of the vectors to scale in the correct orientation. At the same time, the vectors need to be drawn from head to tail. Let's start off with a convenient scale to use. Say 1 centimeter is equivalent to 10 Newton. If we start off with vector A will be drawn 3 centimeter horizontally, and then vector B will be drawn at 5 centimeter with an angle of 40 degrees to the horizontal. Recall that I said that the length of the remaining gap is the magnitude of the resultant vector. That would be this line here, which measured by a ruler will give you 7.6 centimeter. And then the resultant vector direction will be given by the direction from the first point to the last point, which in this case should be pointing in this direction. Now, if you want to describe the resultant force along with its direction, given by angle theta here, by measurement, the resultant force is equals to 7.6 times 10 after taking into account the scale equals to 76 Newton, whereas the angle when measured using a protector will be equivalent to 25 degrees. So this is the resultant force and its direction. Now bear in mind that you can also do the scale vector diagram method by starting off with vector B first. If we use vector B, it will be done like this. You draw vector B at 5 centimeter at an angle of 40 degrees to the horizontal, followed by vector A at 3 centimeter horizontally. The gap will be the resultant. And since this is my first point, and this is my last point, my direction would be in this direction. If I were to use a ruler to measure this resultant, it would be at 7.6 centimeter again. And if I were to measure the angle theta again, it would also be at 25 degrees. So you will notice that this resultant here is actually the same as this resultant here. So it won't matter whether you start off with vector A or vector B, so long as they're drawn from head to tail, you will get the same answer. A very important thing to note is that if vector A is at right angles to vector B, such that they form a right angle triangle with the resultant, it is possible to find the resultant vector by calculating directly using Pythagoras theorem, where the resultant in this case is actually the hypotenuse of the triangle. There is no need to draw a scale vector diagram in this case. Recall that under Pythagoras theorem, for a right angle triangle with sides A, B, and C, C squared is equals to A squared plus B squared, such that C is equals to the square root of A squared plus B squared. Applying it to this example here, R squared is equals to A squared plus B squared, giving us R squared equals to 30 squared plus 50 squared. If we were to simplify all the way to the end, the resultant is actually equals to 58.3 Newton. So please bear in mind that if you see that the vectors form a right angle triangle, you can do the calculations through Pythagoras theorem straight away.